Like in the classroom, prepare yourself for the lesson ahead. Be ready with your materials for math. It is best to have writing materials with you to take down important terms or highlight equations, and in answering the examples discussed. You may use a notebook or a printout of the Learning Worksheet 3.1. Kindly settle down. Algebraic techniques of differentiation. Differentiation is finding the derivative of a function. If you are asked to differentiate, we have learned from the previous module that the derivative of a function, written as f prime of x, is equal to the limit of the quantity f of x plus h minus f of x all over h as h approaches 0. From the introduction to calculus, the derivative is the rate of change, or how the y values change as x changes, just like in the slope of a linear function. For nonlinear functions, we considered any 2 points xy and x sub 0, y sub 0 on the graph of f. And if the 2 points get closer to each other, it means that x approaches x sub 0, and the rate of change is the limit as x approaches x sub 0. This may be generalized by expressing the difference in the x values as h, and x approaching the other value x sub 0 is the same as h approaching 0. Note that f prime of x is the derivative at any point xy, which results to an expression, while f prime of x sub 0 is the specific rate of change at x sub 0, thus resulting to a real number. Let us apply this definition in determining the derivative of a constant function f of x equals k, where k is any real number. F prime of x is equal to the limit as h approaches 0 of the quantity f of x plus h minus f of x all over h. Since f of x is equal to k, f of x plus h is equal to k as well as f of x. Hence, we are only looking for the limit as h approaches 0 of 0 over h, or just 0. Note that we were able to simplify the expression to 0 before evaluating the limit. For our first rule, if f of x is equal to k, then f prime of x, or its derivative, is equal to 0. Let us now find the derivative of the power of a variable. Given f of x equals x to the n, f prime of x is equal to the limit as h approaches 0 of the quantity x plus h raised to n minus x raised to n all over h. To expand this expression, we will need the binomial theorem for x plus h raised to n. You may refer to your trigonometry and analytic geometry or pre-calculus book for the formula. Applying the binomial theorem, x plus h raised to n is expanded into a polynomial with n plus 1 terms with x to the n as the first term and h to the n as the last term. X to the n minus x to the n is equal to 0, thus rewriting the expression with all remaining terms having a variable h. With h in the denominator, we can cancel h from the first term. The second term will now just have h instead of h squared. The second to the last term will have h to the quantity n minus 1 or n minus 2. And the last term will have h to the quantity n minus 1. After canceling h, what remains is this polynomial with all terms still having the variable h except for the first, which is n times x raised to the quantity n minus 1. As we evaluate the limit by substituting 0 to h, all terms will be equal to 0 except for n times x raised to the quantity n minus 1. This proves that if f of x is equal to x to the n, where n is a real number, then f prime of x is equal to n times x raised to the quantity n minus 1. For the next function, we are given f of x equals k times g of x. Applying the definition of a derivative, f prime of x is equal to the limit as h approaches 0 of the quantity k times g of x plus h minus k times g of x all over h. We can factor out k, and from the limit laws, f prime of x is equal to k times the limit as h approaches 0 of quantity g of x plus h minus g of x all over h. We recognize that the limit of quantity g of x plus h minus g of x all over h as h approaches 0 is equal to the derivative of g of x. Therefore, f prime of x is equal to k times g prime of x. We have proven that if f of x is equal to k times g of x, where k is a real number, then f prime of x is equal to k times g prime of x. Moving on, let us consider the sum or difference of two functions. We focus first on f of x equals p of x plus q of x. Using the definition of a derivative, f prime of x is equal to the limit as h approaches 0 of p of x plus h plus q of x plus h minus p of x plus q of x all over h. If we group together terms involving function p and those involving function q, we obtain the limit as h approaches 0 of p of x plus h minus p of x plus q of x plus h minus q of x all over h. If we apply the limit law on sum of functions, we obtain the limit as h approaches 0 of p of x plus h minus p of x all over h plus the limit as h approaches 0 of q of x plus h minus q of x all over h. At this point, we recognize that these limits are equal to the derivative of p and the derivative of q. Therefore, f prime of x is equal to p prime of x plus q prime of x. Following a similar proof, we will be able to show that if f of x is equal to p of x plus or minus q of x, then f prime of x is equal to p prime of x plus or minus q prime of x. We can combine these rules involving a constant, a power, a constant multiple, and the sum or difference of functions to find the derivative of a polynomial function. For our first example, differentiate the function a of x equals 7x to the 5th plus 29x to the 4th minus 15x cubed plus 3x squared minus x plus 31. Write your answer on your paper. Applying what we have learned, a prime of x is equal to 7 times 5 or 35 as the numerical coefficient times x raised to the exponent 5 minus 1 or 4. For the next term, we have 29 times 4 or 116 times x raised to 4 minus 1 or 3. Next term is negative 15 times 3 with a numerical coefficient of negative 45 and x having the exponent 3 minus 1 or 2 plus 3 times 2 or 6 times x raised to 2 minus 1. The derivative of negative x is negative 1 times x raised to 1 minus 1 or 0, and the derivative of the constant 31 is 0. Given f of x equals p of x times q of x, by definition, f prime of x is equal to the limit as h approaches 0 of p of x plus h times q of x plus h minus p of x times q of x all over h. Since there are only two terms in the numerator, and unlike in addition wherein we were able to regroup some terms, here we will be required to add and subtract a particular expression, which is p of x plus h times q of x. With these added terms, we can factor out p of x plus h and q of x. We can then apply the limit laws on product and sum of functions. Evaluating the limits, we obtain f prime of x equals p of x times q prime of x plus q of x times p prime of x. In other words, the derivative of the product of two functions is equal to the derivative of the first factor times the second factor plus the derivative of the second factor times the first factor. Given this product of two binomials, you can choose to expand resulting to a polynomial or apply the product rule. We first get the derivative of the first factor, thus we have 8x cubed, and multiply it to the second factor, 5x cubed plus 6x. For the second term, we get the derivative of the second factor, which is equal to 5 times 3 times x to the 2 minus 1, or 15x squared, plus 6. And multiply to the first factor, 2x to the fourth minus 1. For the next operation, we are given the quotient of two functions. Given f of x equals p of x over q of x. Applying the definition of the derivative and the strategy similar to the one used in the proof for the product rule, we are given that f prime of x is equal to p prime of x times q of x minus q prime of x times p of x all over the square of q of x. To remember the quotient rule, for the numerator, we find first the derivative of the numerator, p of x, times the denominator, minus the derivative of the denominator times the numerator, all over the square of the denominator. In this example, c of x is equal to 2x cubed over the binomial 24 minus 5x squared. To find its derivative, we start with the derivative of the numerator, which is 6x squared, and multiply it with the denominator 24 minus 5x squared. For the second term, we get the derivative of the denominator, which is 0 minus 10x, times the numerator, which is 2x cubed. And for the denominator, we get the square of 24 minus 5x squared. The definition is also applicable to trigonometric functions. Given f of x equals cosine of x, f prime of x is equal to the limit as h approaches 0 of cosine of x plus h minus cosine x all over h. Do you remember what cosine of a sum is? It is equal to cosine of x times cosine of h minus sine of x times sine of h. We can rewrite the terms in the numerator and group those with the term cosine x and apply the limit law for difference of two functions. Factoring out negative cosine x and applying the limit law for product of functions, it results to the limit of familiar trigonometric functions. Recall that the limit of quantity 1 minus cosine h all over h as h approaches 0 is equal to 0, thus making the first term equal to 0, while the limit of sine of h over h as h approaches 0 is equal to 1. resulting to the limit of sine of x as h approaches 0, which is equal to negative sine of x. We conclude that if f of x is equal to cosine of x, then f prime of x is equal to negative sine x. A similar proof will show us that the derivative of the sine function is the cosine function. In determining the derivative of the tangent function, we consider that it may be expressed as sine x over cosine x. And with this, we can apply the quotient rule. The derivative of the numerator sine x is equal to cosine x times the denominator cosine x minus the second term, which is the derivative of the denominator, which is negative sine x, times the numerator, which is sine x. And the denominator is the square of cosine x. Simplifying the numerator, we get cosine squared of x plus sine squared of x, which is equal to 1. And we know that 1 over cosine is equal to secant. The derivative of d of x equals tangent of x is equal to d prime of x equals secant squared of x. At this point, we know that the derivative of the cosine function is negative sine. The derivative of the sine function is cosine function, while the derivative of the tangent function is the squared of the secant function. Lastly, let us consider the exponential function f of x equals e to the x. Based on the definition, f prime of x is equal to the limit as h approaches 0 of e to the x plus h minus e to the x all over h. Rewriting e to the x plus h, we have e to the x times e to the h. We can then factor out e to the x from the terms in the numerator and apply the limit law on the product of two functions. We learned that the limit as h approaches 0 of the quantity e to the h minus 1 all over h is equal to 1. Evaluating the limit, we are able to show that the derivative of f of x equals e to the x is also y equals e to the x. Let us now summarize the rules on derivatives that we have covered. The derivative of the constant function is always 0. Given the variable raised to an exponent, its derivative is the exponent times the variable raised to the original exponent minus 1. If a function is the product of a constant times another function, then its derivative is the constant times the derivative of the other factor. The derivative of the sum of two functions is the sum of their derivatives. Similarly, the derivative of the difference of two functions is the difference of their derivatives. The derivative of the product of two functions is the sum of two terms, each equal to the derivative of one factor times the other factor. The numerator of the derivative of a quotient is the difference of two terms. The first term is equal to the derivative of the numerator times the denominator, and the second term is the derivative of the denominator times the numerator. The denominator of the derivative is equal to the square of the denominator of the original function. For the trigonometric functions, The derivative of the sine function is the cosine function. The derivative of the cosine function is the negative of the sine function. And the derivative of the tangent function is the square of the secant function. We have also shown that the derivative of the exponential function f of x equals e to the x is also y equals e to the x. Please refer to Learning Worksheet 3.1 and the textbook for additional examples. Similar problems and applications are found in the textbook.